We got Laurel in the house. We got David Engelhart. I'm putting my phone on stun. We got Steve. Laurel's in the house, so we have research here. We can get things done now that we got the right people and players. Okay, here we go. Whew, all right, welcome. And we are going to continue our discussion on ampacity. So, Steve is in the house, David Engelhart is in the house, and we have research, Laurel. I got a text from Robert from Omaha, and I got to follow back up with him. I hope he's doing well. So, are you ready for another discussion on mastering ampacity? Okay. So we're developing our PowerPoint slide deck, our educational material for ampacity. Remember, I still have some outstanding things. I'm still not sure I like circuit ampacity, but that's okay. We know what the definition of ampacity is. We've established up to this point, there is a distinct difference between a conductor's ampacity and the limitations of the termination. We've established that separation. We do one, we do the other. Whichever one requires the smaller overcurrent protective device is the one you go with. And at times I may have to increase my conductor size to ensure that I have the right combination of overcurrent protection, termination, conductor size, or overcurrent protection and conductor size to accommodate the ampacity of the conductor and the limitations placed upon that conductor based upon the termination. Now, so we went through to Article 210 and we went through Article 215. We developed, and I've gotten better with my spreadsheet. So, and when we get done, I am going to make this available. Again, this is I'm just want to put it over here. This is, I'm going to work in some more, because today we're going to talk about the services. So what I wanted to do is just show you where I'm at with this spreadsheet. I've got anything that's in the powder blue is where I enter data. So I have my continuous and my non-continuous load. It all starts there. You have to understand what is continuous, what is non-continuous, what portions of your load. If it's all continuous, if it's all non-continuous, we've got to figure that out. I calculate the total load. I calculate 1.25%. So this is 210 and Article 215 have the requirements for the minimum branch circuit ampacity that it has to be greater than one of two different calculations. This is the calculation for the 125% rule, which is 125% times the continuous plus non-continuous. And then this is where you put the temperature rating of both ends of the conductor. So I have terminal 1 and terminal 2. If, for example, we'll play with the first one and we'll make it a continuous load of 99 amps. I know what my total load is. I know what my 1.23 times 99 is. If I say terminal 1 is 60, and what are my options? I have 75, 60, and 90. So if I say it's a 60 degree and the other one is 75 degree, then I know I'm limited by the 60 degree column. My conductor insulation, I can pick different insulation sizes, but nope, actually I hard coded that one in at 90. So I have to turn this to white because it's not selectable at this point. This spreadsheet is based on 90 degree C insulation. The number of conductors in a raceway, and what you'll see is if I said 4, the multiplier goes to 0.8. If I said 15, the multiplier went to 50%. If I said 36, the multiplier went to 40%. So I based the number of conductors in a raceway. I imported the tables from, or I mimicked the tables from the code. So I'm just gonna say, remember the cutoff is 4. So if I said 1 conductor, it's still a 1.0. If I said 2 conductors in a raceway, it's still 1.0. If I said 3 conductors, it's still 1.0. The moment I go to 4, it goes to 0.8. So I'm going to keep my number of conductors at 3 for standard conditions of use. My ambient temperatures, I did the same thing. I brought in the table from Article 310, 310.15, I think it is. There's the ambient corrections factors. So if I go, for example, 100 degrees, I'm at 0.91. If I go 200 degrees, I'm, 100 degrees, I'm not going to 200. So here's the options, up to 185. So if I go to 185 degrees, I'm at 0.29. So I'm going to be at 86, which is 1. 70, let's see, let's try, these are in ambient, ambient in degrees Fahrenheit. So that's the other thing I did, was I did it in degrees Fahrenheit. So degrees Fahrenheit. All right, so I've got my ambient correction. So these are my conditions of use, which is basically the ampacity, that's 99. So my conductor ampacity has to at least be 99 amps. The larger of the two is 123.75, which means my 1.25 is the larger of these two, whether it be 99, which is based only on conditions of use, or 125% without the conditions of use. The larger of the two is 123.75, so now I know my minimum circuit ampacity for Article 215 and 210 for feeders and branch circuits, or branch circuits and feeders, Article 210 and 215. The minimum conductor size has to have an ampacity of at least 123.75. And then I do the calculation. I go into the conductor. So that would be a minimum size of a 2 gauge copper or a 1/0 aluminum. And that's based upon the 90 C column of those conductors in 310.16. So then I pick the size, so whatever in blue. So I'm going to pick the size. If I say I'm going to put a number 2, because that's the minimum size, and I'm going to be cost conscious, and I want to go to the smallest conductor that I can go to based upon those 2 calculations. I'm going to pick copper. My equipment temperature basis is 60 degrees because, remember, one of my 2 terminals, and what 110.14 tells you is you've got to go by one of the lowest terminal temperature ratings. And that means my equipment, to protect my equipment, my circuit breaker or my fuse, has to at least be 95 amps. I can't go to the next higher to 100. I can go down to the next lower based upon the standard ampacity values. And then my 90 degree C is, that's the 90 degree C column. That tells me my conductor has an ampacity based upon conditions of use, which is based upon the 90 degree C column of 130 amps. So as you can see here is, I have more conductor than what my termination can handle, if that makes sense. That's the number of conductors I have in parallel. So this is my evaluation. So what these 3 values tell you is what's the minimum circuit breaker or maximum circuit breaker size. For the first one, the overcurrent device has to be greater than or equal to 125 amps. So I can't put a 100 amp circuit breaker on here. I have to go to at least 125 because it has to be greater than or equal to 125% of the continuous load. I should put the code references in here. I will do that. Column X is my equipment protection. That tells me my circuit breaker has to be less than or equal to the next lower from a 95 degree. Remember, this was 95. My next lower standard ampere rating is a 90 amp circuit breaker. So my circuit breaker has to be less than or equal to 90 amps. And I can immediately see I've got a problem because my minimum circuit breaker size has to be 125. My maximum circuit breaker size for the equipment is 90. I got a problem that I'm going to have to solve. And the only way to solve that is to increase the conductor size. And then my ampacity, to protect the conductor at its ampacity, I have to be no greater than 150 amps because I can go, based on 240.4b, with an ampacity of 130 amps, I can go to the next larger overcurrent device. So my problem with selecting this conductor is probably going to be in this range. So I'm going to pick, since it's a 90, I'm going to pick a 90 amp circuit breaker or fuse, and I'm going to make, and the conductor size is already, I said it's a number 2, and then this is where I do my values. Do I have an ampacity issue? I don't have an ampacity issue. Am I protecting my equipment? Yes, I am, with a 90 amp breaker. Am I over 125%? I'm not. My load, I'm not good enough with my load, so my breaker's 90 amps, my total load is 99 amps. I'm going to trip the breaker just on overload if I selected the minimum size. So regardless of the equipment protection, regardless of the 125%, I can handle a total load of 99 amps, okay, with that conductor. So that means I'm going to have to increase this conductor size. I'm going to go to the next higher. I'm going to go to a 1 gauge. So now my equipment protection goes up to 110, so I can put a 110 amp breaker. My ampacity is 145, so that means I can go to 150. There's my 150 or less. So a 110 amp breaker would protect the equipment. It would not be greater than or equal to 125%. So I'm going to try a 110 amp breaker because that's my minimum. And everything is good except I'm not over 125%. So now I still have to go higher in my conductor size because I can't increase the breaker size to the next higher because I'm at my limit to protect the equipment. So then I come back over and I change my size of my conductor to a 1/0. And that tells me that my equipment is 125 amps. That means I can use a 125 amp breaker. My 125% is 125 amps. And my ampacity or next has to be less than the next larger, which is 175. And 125 amps is less than the ampacity of the conductor. So if I pick a 125 amp breaker, all of this should be fine, and it is. Boom. So that's how I use this spreadsheet. Now, I did account for small conductors. So if I said, for example, this was a 18 amp load, and I said my minimum size conductor can be a 14, and I selected a conductor. Why is it doing that? I got 86. Why can't I pick? Ignore error. I'm going to change this to, the minimum size is a 14 copper. So if I go to a 14, now it tells me what my equipment temperature is 60 degrees C. My equipment is 15 amps. That means that I need a 15 amp breaker. If I select a 15 amp breaker for my 60 degrees C column, it says it is a small conductor and it tells me my required overcurrent device is 15 amps. But 15 amps is not over 125% of my load. So then I would have to increase the size of the conductor. So I did address the small conductors in here, but what I didn't address is the topic of today, which is our service conductors. Now, service conductors can present a little bit of a challenge, right? So let me do this. I've made some changes to the slide deck a little bit, and I've got a 3-step process. And that is for, this is for Article 210 branch circuits. I have the process identified for Article 215 feeders. And now I have Article 230. So our discussion today, so that was my recap. Okay. Laurel says, welcome, well worth the effort to program the spreadsheet. Yep, I'm going to put the code references in, and Laurel, I will share this. So I'm not about, as we develop this, and what we're doing is we're verifying it. So all of the information in the entire process, I'm going back to the UL standards for how we test the products to make sure that I'm not going to pick a combination that violates the UL listing. That's a very critical piece of the puzzle. We want to make sure that the installation requirements align with how we list and test the products. So as I'm going through this, and even in the slide decks, and we saw this over the last few sessions that we've had, I am comparing the requirements, the selection of our conductors, and the code rules, following the code rules, and going back to the product standards to make sure that we're all in alignment. All right, so let's talk about Article 230, because there is a section in there. I was talking to a gentleman about what I'm learning here on Ampacity, and I was like, boy, I'm seeing a mistake that could happen legitimately, where we mistakenly use the 75 C column to say that's the ampacity of the conductor, and then go to the next larger size overcurrent device, which would go against how we test products, and it goes against the UL listing and all that jazz. And then they said, well, what about service conductors? Because that violates this too. And I said, look, I'm covering Article 210 and 215. I haven't hit services yet. That starts today. So let's take a look at 213. 230.42 is going to be a key code reference for us. What it says is 230.42 is titled minimum rating and size. So I have one issue right now I can see. Rating is a bad word when it comes to conductors, because conductors don't have a rating. They have a ampacity. So what I'm going to do is, this is going to have to be a code. It's going to be after code change. I'm going to have to make a code requirement change. 100% rating. And let me put it in white. Change this to minimum ampacity and size. All right, so that'll be a public input. We're going to have to make a public input for Article 230 in Section 230.42 to change the, and because then that would align with, if I go back up to feeders, minimum, ooh, that's rating and size too. That's got to change. And let me come back down here. These are all public inputs for the next edition of the code. Change to ampacity, and let's go to 210. 210 is minimum ampacity and size of conductor. Conductors, minimum ampacity and size. So we did it right in 210. We didn't do it right in 215, and what we should do is make them align. Conductors dash minimum ampacity and size. So let's go down here. Conductors dash minimum ampacity and size, and let's do ampacity. And we're going to underline this. Hey, there we go. You know what? You're right, Dawn. You're right. That's another good change. Minimum ampacity. And I'm going to do this. If you have ampacity, you don't need size. I like that. Let's go back up. Go to the language, the title, branch circuits, minimum ampacity. Strike that out. Boom. And Control V. If you have ampacity, you don't need size. I'm going to put that here. And put it here. Conductors, minimum ampacity. That's branch circuits. We just did feeders. And if we go to services, we can say conductors, minimum ampacity. See, that is the value of doing this as a team. Strike that out. I say we change that to this, and then we do a copy, bring that down. If you have ampacity, you don't need this language. Right? I like it. Okay, so queso, that's cheese. So we got 230.42 conductors, conductors dash, which is new language, minimum ampacity. Oh man, it's beautiful, Dawn. Beautiful. I like it. I like it. I like it a lot. All right, so this says service entrance conductors shall have an ampacity of not less than the maximum load to be served. So, and it tells you how you calculate the load. You have to determine the load based on part 3, 4, or 5 in Article 220. Then, it requires that we conduct 2 different calculations, one considering only 125% of the continuous loads, and we know we saw that before, right? We saw this in 210 and 215. 125% of the continuous load, and one considering only the conditions of use, which we're going to fix that too in the language, Dawn. That public input or public comment last cycle, I say last cycle, the 2026 code, that should have passed. I should have fought harder at the code panel for that language. Unfortunately, I guess I was beaten to a pulp on other things, and I'm going to fight for that one next cycle. Requires that we conduct 2 different calculations. Okay, and then they have a reference made to 110.14c in the parent text for compliance, which reminds us that the circuit will be limited by the termination. All right. I've got a public input I'm working on, and I'm thinking I've got it in the wrong section. But in any case, forget it. All right, so 240.4 says, conductors other than flexible cords, flexible cables, blah, 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 and in H, dwelling unit service and feeder conductors. And it says, dwelling unit service and feeder conductors shall be permitted to be protected against overcurrent at the ampacity values in 310.12. So now that's telling me to go to 310.12, and I'm permitted to use those values to protect those service conductors. So I have it twice. I don't know why I have it twice, but I've got it twice. I don't have it thrice, so that's good. Here's 310.12. I'm going to just, let me delete this. I'm going to delete this one because I don't see any value in that. 310.12. The parent text of 310.12 says that it applies only to one-family dwellings, the individual dwelling units of two-family and multifamily dwellings. It applies to service and feeder conductors that are supplied by a single-phase 12240-volt system. So what it's doing is it's narrowing the focus of where this applies. You just can't apply it to all service conductors, only those for one-family dwellings or individual dwelling units of a two-family or multifamily dwelling, service and feeder conductors supplied by a single-phase 12240-volt system. So if you have a one-family dwelling unit and it's a three-phase supply, I mean, I'm sure someone out there at some point built a home that has a 480 volt service. Bill Gates probably is a good one, a good example. I don't know his house, but if I was him, I would. Anyway, so this limits that to that voltage. And it says Wingle base, Wingle, I think that's single phase feeder conductors consisting of 2 ungrounded conductors and the neutral conductor from a 208Y 120 volt system. So this tells me I can also address feeder conductors. All right, that's the parent text. Now in A, it says services. Services rated 100 amps through 400 amps. Service conductors have, now again, I'm limited by the parent text, so we've set the stage for the requirements found in any first level subdivision under 310.12. It only applies to those applications that we've identified in the parent text. Puts it in perspective. Service conductors must supply the entire load associated with a one-family dwelling or with an individual dwelling unit in a two-family dwelling. They didn't have to put that. All they had to do was say service conductors must supply the entire load, period. That's not needed. And I'll plan it. I can put a public input in because you've already set that in the parent text. The service conductors have to supply the entire load, period. So what that means is I can't, like if I have in this house, I have a meter outside, and from the meter I serve the a main in my panel board downstairs, and it's a 200 amp service. And in my case, the service conductors are supplying the entire load. And it tells me that my ampacity can't be an ampacity not less than 83% of the service rating is permitted. It's not required, it's permitted. So if my service rating is 200 and I have a 200 amp breaker, 80%, because it would be an 80% rated device, 80% of 200 is 160 amps. So if I'm following the rules in 210 and 215 say that I have to take my load and multiply by 125%, which is basically 0.8 times the overcurrent device. This is telling me I can do 83%. So the ampacity of the conductor cannot be less than 83% of the service rating, which is 83% of my 200 amp breaker. Right. And then table 310.12a is permitted to be applied if no adjustment or correction factors are required. So that means if I'm not doing any temperature adjustments, and I'm not, or temperature corrections or adjustments due to number of conductors in a raceway. Has nothing to do with termination. It only has to do with the number of conductors in a raceway and the temperature modifications. Then I can use this table. And what the table tells me is, if I have a 100 amp circuit breaker, shouldn't have done that. If I have a 100 amp circuit breaker, I can put a 4 gauge conductor on it. And so what I'm saying are those size conductors for service applications violate our previous findings, right? So if I have 175 amps, a 175 amp circuit breaker on a 1-aught, protecting a 1-aught conductor. I can't do that based upon what we just talked about, the last 4 sessions, right? So, but I'm allowed to do it here. So here's my concern is, why am I allowed to do it here? That's my first question. And second, does that violate the UL standards? So what I did, so that's where my head is at, because that was what I had someone comment to me. They said, well, wait a second, Tom, what you're saying is fine, but how do you explain service conductors? And so I explain things through product standards and how we test them, because we are codes and standards. So if I go to, and I'm just pointing out the fact that in the 75-degree column, it's 115 amps on a 125 amp breaker. If I just do a 125 amp breaker times 0.8 for 80%, my 75-degree C column is greater than, it's 100 amps, that is greater than my 1.25. And, oh, actually, no, I'm thinking about that wrong. My 125 amp breaker has to be less than what the 115 amps. So for me to protect the circuit, right? Not at the ampacity. The ampacity and the load has to be, I have to be 1.25 over the load. That's already covered. But this is dealing with the protection. I'm concerned now with the protection of the equipment at 115 amps, because what we said earlier, what did we say earlier? We said earlier, oh, let's go to the spreadsheet. Here's what we said earlier. We said, I'm going to take 100 amps. Let's do this. I'm going to make this 100 amps. If I have a 100 amp load, in the standard conditions of use, the larger of the two is 125 amps. My minimum size conductor is a 2-watt. If I pick a 2-watt conductor, that tells me my equipment has to be protected at 145 amps. And what was our number? We have 125 amps. So let's do this. 125 amps. What is 0.8? 100, yeah, it's 100 amps. All right, so this is telling me that I have 115 amps, and my overcurrent device is greater than the 115. If I had this situation and I had 114 amps for a 2-watt conductor, what size was this? This was a number 2 gauge. Let's put a number 2 in here. What's a number 2? Ignore error. What's a number 2? A number 2 tells me my overcurrent device would have to be a 90 amp breaker. But I'm not putting a 90 amp breaker on a number 2 copper. I'm putting a 125 amp breaker on a number 2, on a 2 gauge copper. That violates what we just said. We said for branch circuits and feeders, I can't go greater than what the termination permits. I think I have 60 degrees. I got to change that to 75. I got to change it to 75. Because we're dealing with 75, so let me go back. It's 115. So I have 115 amp for a 2 gauge conductor in 75 degree C equipment. I've got 115 amps. That would tell me that a 110 amp breaker would be fine. But I don't have a 110 amp breaker, I've got a 125 amp breaker. So I'm putting a 2 gauge on a 125 amp breaker, and that is ungood. I would need to have that on a 110 amp breaker for it to be adequate. Based upon everything that we've talked about so far, which is based upon how we test products, the UL standards. So, to that end, I went to UL 67 and said, okay, how do we test circuit breakers, and do we test them, or how do we test in the application for service equipment? How do I test it, and does it line up with this? Because if it doesn't, I've got a code problem, or I need a standard change. So if I go to the standard, I'm going to go to the standard, and I'm looking for, there's a table in here that we use for the voodoo that we do so well. Where's it at? Here it is. The She Blows, Cupcake Island. How do I zoom? Here it is. All right. So now this is 100 amps to 400 amps, which is a number 4 all the ways up through a 400, right? So number 4 through 400. Let's go to the language. What is this? Hold on, let me go back up. A number 4 to a 400, right? God bless you. So now I come over here for a number 4, and I see my copper 70, aluminum is 55, and there's my 85. This is for my 75 degree C column. I've got 85 amps. But look at the parens is 100. That says 100. Let's go back to the code language. A 4. A 4 is on a 100 amp breaker. So if I come back over to the product standard, I have a 4 gauge conductor, and there's the 85, and then there's the 100 with parens and a note C. If I go down to note C, note C says, the values in parentheses are capable of being used at the main terminals of a single-phase 3-wire panel board intended for use as residential service equipment when the panel board is marked in accordance with 34.1.14. So that lines up, and that would mean that we are testing these service panel boards with those size overcurrent devices, with that size conductor, which lines up with these values that are in table 310.12a. I don't have a problem with the code language because it lines up with how we're testing the product. Now, if I would say, oh no, you can go to the next higher overcurrent device and protect that number 2 with a 150 amp breaker, now I got a problem, because now you're not only violating the UL standard, because I don't test a 150 amp breaker with a 2 gauge conductor on it. And because this table is so explicit and direct, I would also be violating table 310.12a, which specifically tells me for a 150 amp breaker, I need a 1 gauge. For a 125 amp breaker, I can have a 2 gauge. I can go higher, I can go larger, but I can't go smaller than that value. So what I do in this slide deck is I'm identifying, there's my gauge, and there's my my conductors. I'm acknowledging the fact that this doesn't quite line up with what we said before. And I point out that, look, you know, the 125 amp breaker should be less than the termination rating of 115 amps. So that is ungood. And then I go to the table 11.1 in the code, and I highlighted, there's my 4 through 400, and there are my 100 amp through 400 amp overcurrent devices. There's the parens. The values in parentheses are capable of being used at the main terminals of a single-phase 3-wire branch and panel board, and they basically put the similar parameters that is in the code that basically narrows our focus. And then I have my 31.1.14. It says, if one of the current values given in note C is employed as a rating of a single-phase 3-wire panel board, the panel board shall be marked to indicate that this rating is applicable only if the panel board is installed as a single-phase 3-wire residential service equipment. So the code requirement aligns with the standard, and that is utopia. We've got to make sure that our our NEC requirements align with how we list and test the products. So that check is well worth making. That process is very critical and important to ensure, to at least validate. Now I can use this rule every day of the week, twice on Sunday, and feel comfortable and confident that when I apply the requirements in 230 or 310.12, which I'm not sure why it's in 310. Why wouldn't you put the protection of the conductors in Article 230? I think it should be in 230. Dawn, what do you think? It would make more sense to me because we have the conductor protection requirements for branch circuits in 210. We have the conductor protection requirements for feeders in 215. You would think that we would have the minimum circuit ampacity and the conductor protection all in 230 for service conductors. Why is it back here in 310? What do you think about moving the 310.12? Let's take a look at where's 310.12. 310.12. Here's 310.12. So it says installation, uses permitted. This is conductors for general use. This is uses permitted, and then it says single-phase dwelling services and feeders. Service and feeder conductors supplying by a single phase shall be permitted to be sized in accordance with. So it talks about the sizing and the protection of service and feeder conductors. The feeder stuff should be over in 215, and to say when a feeder supplies a dwelling unit and the entire load of a dwelling unit in multifamily and two-family or multifamily dwelling units, then this is how you protect it, and you're permitted to protect it this way. And then in 230, it should say for services that supply for one family. I tell you what, this is a public input waiting to happen, in my opinion. Why is it in 310? What does it have to do with conductors for general wiring? Dawn is saying 310.12 changes the ampacity of the conductors for dwelling services. It is a ampacity rule and belongs in 310. It changes the ampacity. So it doesn't change the ampacity. How does it change the ampacity? I'm just trying to understand this. Yes, it's a Wired Wednesday, Willie. It's a Wired Wednesday. So this says single-phase dwelling services and feeders. This is, so the table 310.12 is not an ampacity value. It tells you a conductor size and the service rating. Tells you the conductor to use. Doesn't tell you how to, it doesn't change the ampacity of a conductor. I don't believe it does. So 310.12 says, 310.12 says, for one family dwellings and individual dwelling units of two family and multifamily dwellings, service and feeder conductors supplied by a single phase system shall be permitted to be sized. So it's how to size service and feeder conductors. For one family dwellings and individual dwelling units of the two family single phase feeders consisting of two blah 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 shall be permitted to be sized in accordance with 310.12 A through C. So A is services. For services rated 100 amps through 400 amps, the service conductor supplying the entire load and the service conductor supplying the entire load associated with the individual dwelling unit, blah, 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 shall be permitted to have an ampacity not less than 83% of the service rating. So that's a minimum That's a minimum ampacity rating. No different than what we do in 210 and 230 or 215, in my opinion. If no adjustment or correction factors are required, then you can use these conductors. I get it. Willie says you can have a 2-aught conductor to feed a 200 amp service. Yeah, that's what we just said. As long as you meet the requirements. There it is right there. There's a 200 amp overcurrent device and you have a 2-aught copper. You can't have a 2-aught aluminum, but a 4-aught aluminum. And that is for services as long as, Willie, as long as you meet the requirements that it is a 120 240 volt system and it is for a one-family dwelling and the individual dwelling units of a two-family or multifamily dwelling. So it has to supply the entire load. As long as you meet those requirements, then yes, I agree with you 100% because it's right here in black and white. But now feeders, for a feeder rated 100 amps through 400 amps, the feeder conductor supplying the entire load associated with one family dwelling or the feeder conductor supplying the entire load associated with an individual dwelling unit. Okay, shall be permitted to have an ampacity not less than, so this is again a minimum ampacity. And it's permitted, it's not required. It's permitted. If no adjustment or correction factors, then you use that table. In no case shall a feeder or an individual dwelling unit for an individual be required to have an ampacity greater than. So that's again, that is very similar to a minimum size. And then the grounded conductor. So all of this language, in my opinion, I'm just giving you my opinion. Don't you think it needs to be here in 310? I think it can be over in 230. Now see 110.14 Charlie 1. Now 110.14 Charlie 1 doesn't have anything to do with the ampacity of the conductor. It's all about the rating. And what it does tell you, the rating of the termination, right? So the maximum current you can put through a termination. And the reason it points to this section in 110.14 is because it violates 110.14, right? Ooh, David, I like to say when it feeds the entire diversified load. I like what you're saying there, and I agree with you 100%. And that's probably a reason why you can do that and why it's permitted, and we test it that way. But the reason that 110.14 points over here is because of what I said earlier. It violates the fact that your overcurrent protective device that's in this column, the 100 amp breaker protecting a 4-gauge conductor, doesn't add up based on 110.14. That's why you need the exception in 110.14. In 110.14, open in a new tab. You need that exception in 110.14 because 110.14 would tell you you can't do what that's telling you that you can do. Right? So let's take a look at 110.14. It tells you in C, it says the determination, blah, 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 blah. And it says table 310.16, which is that 75 degree or 60 degree column, but as appropriately modified by 310.12. So it's telling you, you don't have to protect it at that value. In 75 degree C column, you can actually put a larger overcurrent device than what's in the table for that termination. And what gives you that permission is only what's in 310.12, and to Willie's point, only if you meet the requirements of the parent text. If it's a single phase, if it's got the right voltage ratings, if it's serving the entire load, all of those conditions, if you meet those conditions, then you can put that smaller size conductor on the overcurrent device, which would not be permitted in 110.14 C1. So that's the tie-in. That's why they had to put it there. It's because you're violating 110.14 C1 right here, as we identified right here. If I put a, what size? We picked a 4-gauge copper, 4-gauge conductor protected by a 100 amp breaker. If I put a 4-gauge conductor, a 4-gauge, and I change this overcurrent protective device to 100 amps, 100 amps has to be less than or equal to the equipment. That 75 degrees C equipment, it has to be less than 85 amps. So I would have to put like an 80 amp breaker on it if one existed. What are the standard breaker sizes? 85? Yeah, I'd have to put an 80 amp breaker on that. If I don't have an 80 amp breaker, I'm not protecting the equipment. Now, forget about the load, but that is a no. If I put this down to an 80 amp breaker, boom, I'm now protecting the equipment. And that's all based on 240. So what I've got to do in my spreadsheet is I have to add, insert. Is this a service application? Is this a service conductor? Right? And I would do a yes, no. I'd have to do a yes or no answer here. And then I would modify my equipment because my equipment protection level would change. The termination would change. The ampacity of the conductor is always the ampacity of a conductor. If I have whatever the ampacity is, it is based upon conditions of use. What 310.12 is doing is it's telling me for that breaker, I can put a smaller size conductor than what's permitted in 110.14. And it's not because of the ampacity of the conductor. That conductor, a 4-gauge conductor, if I look at a 4-gauge conductor, that conductor, based upon conditions of use, can take 95 amps. Is that right? 95 amps. Oh, yeah. And I'm going to the next larger overcurrent device, which is 100. So I'm protecting the conductor by its ampacity. That's beautiful. That's beautiful. So a 4-gauge conductor has 95 amps worth of ampacity. What Article 240.4b says is I am permitted to go to the next larger overcurrent device for protection of the conductor at its ampacity. What this table is doing is not changing the ampacity of a 4-gauge conductor. This table is letting me put a smaller conductor on the terminal, which is modifying 110.14. What's the title of 110.14? That is the equipment temperature, the electrical connection rating, the temperature limitation for that service disconnect. So I'm not changing in 310. In 310, I'm not changing the ampacity of the conductor at all. The ampacity of that 4-gauge conductor is what it is. And remember what this says, as long as there are no adjustments or correction factors, that means the conditions of use are what's in 310.16, which is what I have here. And the ampacity of that conductor, based upon the conditions of use for a 90 degree C insulated conductor, is 95 amps. And that table is telling you you can protect it with a 100 amp circuit breaker because that's the next larger overcurrent device. And that hasn't violated Article 240. It hasn't violated 240.4. I'm protecting that conductor at its ampacity. What I'm not doing is I am not meeting the equipment protection in 110.14. So in 110.14, I need a note that says, hey, you're going to have a larger overcurrent device than what 110.14 permits, which 110.14 would tell you your overcurrent device can't be greater than 85 amps. But 310 lets you do it for these specific service applications when you meet those specific criteria. It is dovetailing together. Willie says, I would personally run a 500 kc mill because code is just the minimum and I'm no hack. So you would put a larger conductor size than what the code permits, and you're permitted to do that. You are permitted to do that. You are permitted to go and exceed the bare minimum requirements. I would encourage people to do that. In many applications, I do. Because to your point, Willie, you know, like me, I put ground fault circuit interrupters where I don't necessarily require them. It's above and beyond. I'm not a hack, right? Smiley face. But, and I know you agree with that as well. So that is, I like this. I like this discussion because it really helps. It really helps solidify the marriage with 110.14. 110.14 deals with the termination and the equipment rating. And I don't like to even say termination because I can have a terminal in equipment that's rated 75 degrees C and the terminal is 90 degrees C. Just because I have a 90 degrees C lug does not mean that I can land a 90 degrees C conductor and use it at its 90 degrees C ampacity. I could buy a 90 degrees C lug and put it on that device if I wanted to, right? But that doesn't mean I can now use a 90 degrees C conductor at its 90 degrees C insulation. It's the overall equipment rating because, especially when it comes to panel boards, we have to think about the enclosure size and all of the other components that are associated with that panel board as an assembly, and do they work as a system? And if they work as a system, they're tested as a system, and temperature is one of those aspects of difference between the component standard, because I may be able to get a circuit breaker to pass a thermal test, and say it just barely passes. Say it, you know, hey, I got it through. And then I take that circuit breaker that passed the UL 489 standard for all of its conditions, including thermal, put that into a tight enclosure, and now all of a sudden it fails thermal. Why would that be? Well, because in 489 we tested in open air. But in the UL 67 standard, we have to put that breaker in an assembly. We have to put other devices in there with it. We need to put it in an enclosure. We need to put a dead front on it. And we need to bake it at a certain ambient temperature. And then you need to pass the heat rise test. And that is when things go wrong, because you've put that circuit breaker that you tested in open air as an individual component. Now you've put it into an assembly. And when you put it into an assembly, now you have a different environment for the components, and they will perform differently, especially from a thermal perspective. Man, I tell you what, I like when a plan comes together because it makes sense. You may have already hit that in 110.14 and 110.14 C1B2. 110.14 C1B2. I got to go to the code. 110.14 110.14 C1B2. Boy, C is temperature, 1 is equipment provisions, B, that's your 75 degree, and 2, conductors with higher temperature ratings, provided the ampacity of such conductors does not exceed. Yes, so here's my issue with that language. I'll tell you why I think that language is wrong. I got 2 more people. Steve. Hold on. I'm going to get back to you, Laurel, in a second. I just want to see what Steve says. Steve is saying the temperature rating of equipment as labeled is what it is, period. As listed by the NERDL, yes. And cannot be modified without a field listing. You're absolutely right. It is what it is. You can't take a 90 degree C lug, stick it in and say, it's 90. No, you can't do that. 1,000 points of light, right? I agree with you 100%. And then Willie says, I recently seen equipment marked 75. Yes. Oh, Willie, good point. So you could have a piece of equipment that's rated 75/90. That means that you can use it at 75 degree or 90, and that means that you can use that equipment at the 90 degree C ampacity. That's telling you, whatever that equipment was, I'd love to see a picture of it. I don't doubt that it's out there. I forget who it was. Brian Rock was on one time, and he said it's a unicorn. 90 degree C is a unicorn. 90 degree C equipment is a unicorn. Willie, I think that if anybody comes across that, please send me a picture of it and tell me what it is, because I would love to include that in this educational program. Because here's the thing. If I go from a 75 degree C equipment and I go up to a terminal, like a box that has a terminal block in it, and it's 90 degrees C, and then do another terminal block in a box that's 90 degrees C, that conductor that's in between, I can use that at 90 degrees C, ampacity every day of the week, twice on Sunday. And I don't need a code change to do it, because that is all per existing requirements. I know we made a change in 210 or 215 that says you can do that. Not needed, but we put it in anyway. That's fine. It added clarity, but it wasn't necessarily needed. But Willie, I'd love to see that information. Love it. I love it. And then I'm going to get back to you, Laurel. Hang in there. Steve says what you can do is run 90 degree C conductors and splice. Yeah, there you go. Lower temperatures, larger conductors. There's no NEC guidance for the length of the splice. You're absolutely right. I don't disagree with you, Steve, and that's what I was just saying that, but in different terms. But that splice, I'm not sure where you would have where you would want to do that. I don't think I agree with you. There's nothing in the code that says you can't do that splice inside of the panel board. I don't believe. That transition from the smaller conductor to the larger conductor, I've always seen it done externally. In fact, I think Schneider Electric had a product at one point on the market that was like a transition box. I saw it at an IEI meeting. But I don't, but the key thing was it has to be listed for 90 degrees C. That's the other important thing. I haven't forgot about you, Laurel. Don't worry. And thank you. I'll get a picture the next time I'm on the roof. It's a 7-ton air handling unit. Love it. Can you lift that 7-ton air handling unit with one arm, Willie? I know you're a strong guy, but you never know. All right, so let's go back to Laurel's question. Laurel says you may already have that in 110.14 at 110.14 C1B2. And what she's talking about is this language right here. It says the terminations of provisions of equipment for circuits rated over 100 amps or marked for conductors larger than 1 gauge shall be used only for one of the following. The conductors rated 75 degrees C. And here's the problem I have with 2. It says conductors with higher temperature ratings. I agree with that. Provided the ampacity of the conductors does not exceed the 75 degrees C ampacity of the conductor size used. Well, that doesn't make sense to me. And the reason I say it doesn't make sense is because the ampacity of a conductor is based on conditions of use. It has to do with the number of conductors in a raceway and the temperature. I know what they want to say, but what they're saying doesn't make sense when you understand what ampacity of a conductor is. The ampacity of the conductor doesn't change. It is what it is. It's based upon the conditions of use. If I look at if I have a 90 degrees C rated conductor and I go to table 310.16, if I don't have more than 3 current carrying conductors in a raceway and my ambient temperature is 86 degrees Fahrenheit, the ampacity of that conductor is whatever's in that 90 degree C column. I'm not going to change that. The only way to change that is to put it in an elevated temperature in an ambient, or put it in a raceway that has other current carrying conductors and have more than 4 or 4 or more, right? So for this to say that the ampacity of the conductor cannot exceed what's in the 75 degree C column doesn't make sense. What they mean to say is you've got to protect this conductor. The maximum current allowed over that conductor can't exceed what's in the 75 degree C column. That's what it's telling you. But that's not what it says. Because it says the impact. So if I have a conductor, if I increase the size of the conductor, because I have voltage drop concerns, when I put a larger conductor, based upon those conditions of use, if I go to, for example, if I go to 310.16, Where's 310.16? Let's go to the table. Let's go to the table. 310.18, 310.16. If I go to this table, and I'm going to teach you something. I learned this online from one of you guys or gals. Maybe it was Dawn. You pin header. Boom. And now that stays the same. So when I scroll down here, you got to get NFPA link and exercise this stuff. I'm telling you. So let's say that I have a 1-aught conductor and its ampacity based upon these conditions of use is 170 amps. And I say, you know what? I need to increase this because of voltage drop, and I put a 3-aught in. The ampacity of that conductor is 225. Does that exceed what's in the 75 degree C column? Yes, it does. It will. You can't tell me I can't put a larger conductor. I can't have the ampacity of the conductor be greater than what's in the 75 degree C column. That means that I can't use a 90 degree C conductor. That doesn't make sense. And there should be no provisions in there that says you can't use a 90 degree C conductor on a 75 degree C piece of equipment. You just can't put more than what's in this 75 degree C column through that termination and over the conductor. You can't exceed that value. So I have heartburn with this language right here, which I'm gonna make some public inputs to try to modify this. And I have ideas on what I think it should say, but to tell me that I can't have an ampacity greater than 75 degrees C, I know what they mean, but what they wrote is not what they mean. Okay. Steve, just outside the equipment, J-box. Okay, here we go. Let's go back to Steve. Let's go to Steve. Just outside of the equipment, J-box, and just outside of the source enclosure should pass it. Absolutely. That removes any question in anybody's mind, Steve. You take the conductor at 75 degrees C, off of the breaker, out of the box, go to a junction box on a 90 degrees C termination in equipment that's listed for 90 degrees C. Now we can have the debate on whether or not it needs to be listed. I'm not sure there's a requirement that says it has to be listed, but it should have a rating of 90 degrees C. Go to another box that has 90 degrees C, back down to 75 degrees C, and now that longer run is at a smaller conductor size. All right, then Willie says, is there anywhere in the code where it states a conductor that is rated for 10 amps maximum? Oh, yeah, Laurel's got it right. 240.4, 240.4, Article 240, that's small conductors. Now, what it says is, you know what? Well, here's what it says. If I look at 240.4, what time is it? 12:38. 240.4. We're going to cover this, and then I think we're going to call it a day. 240.4. If I look at 240.4, there's small conductors in D. So what this tells you is, so your question was what? Is there anywhere in the NEC where it states a conductor that is rated for 10 amps max? Here's how I interpret I'm going to do two things. Let me close this out. I'm going to do two things. I'm going to grab 310. So this tells us that a 16 gauge copper, it says 10 amps provided the following conditions are met. The continuous loads can't exceed 8 amps. Now what this is telling you is that you need to protect a 16 gauge copper at 10 amperes. Now your question, Willie, was, is there anywhere in the code where it states a conductor that is rated? It's an incomplete sentence. I guess you're asking, is there anywhere in the code where it states a conductor is rated for 10 amps maximum? 16 gauge is it has to be protected by a 10 amp circuit breaker. If I go to 310.16, a 16 gauge conductor doesn't have an ampacity below the 90 degrees C. It says it's an 18 amp conductor. It doesn't have a 75 or 60 degrees C rating on it. But 240 tells you that that 16 gauge copper has to be protected at 10 amps, period. And that's about short circuit protection for that small conductor. So it tells you that the continuous current can't be greater than 8 amps. That's 80%. So that means I'm going to have a 10 amp circuit breaker, and it's going to be an 80% rated device. 80% of 10 amps is 8. That means I can't exceed 1.25 times 8 amps. Now, what it doesn't do is tell you that the continuous plus the non-continuous. So if I have another 2 amps of non-continuous or an amp of non-continuous, can I put 9 amps on a 10 amp breaker? It doesn't. We're not worried about that. We're just worried about the 1.25 times the 8 amps. And then it says overcurrent protection is provided by one of the following: branch circuit rated circuit breakers listed and marked for use with that. Fuses, or you can use a class CC, class CF, J, or T fuse. So would I say that the NEC tells you that the conductor is rated for 10 amps? I would say no. Nowhere in the code does a conductor have a rating. We removed that a couple cycles ago. Conductors have ampacity, not a rating. It's not a rated ampacity. It's not a rated current. It is an ampacity. The amount of current any conductor can carry is based upon its conditions of use, period. Which the conditions of use consist of the number of conductors in a raceway or the ambient temperature within which it's installed. And there are some exceptions for the ambient temperatures. Oh, well, Willie, okay. All right. I see. So you were going down the 10 amp. I was curious why they have a 10 amp circuit when there's nothing in. There is in the 2026. Actually, there is something in 310. You have to protect it. You have an 18 gauge conductor that is 14 amps in ampacity. We have a 15 amp conductor at 60 degrees C with a 14 gauge, and the 2026 edition is going to have, there were no NIPMAMs or CAMs associated with the addition of a 10 amp circuit in 310.16. So that will be a part of the next edition of the code. Don Ganir. Donnie baby, if those 90 degree C conductors are on a heavily loaded circuit, the owner will be paying for the I2R losses for the life of the installation. Yeah, no, you're right there too. Now here's the thing, Don. Where I think this is Tom's opinion, and remember, my opinions are like some other part of your body. Everybody's got one. In my opinion, those smaller, like a 10 amp breaker and a 15 amp breaker, but a 10 amp breaker especially, when you think about LED loads, here, you know what I'm gonna do? I have my outside lights on a 20 amp branch circuit. I have my outside lights on a 20 amp branch circuit. I'm going to turn those outside lights on. Front lights, okay? I'm turning my outside lights on. These are on a 20 amp circuit breaker in my basement, and they are currently pulling 1.1 amps. Could I get away with a 10 amp circuit on those lights outside? I would have to say yes. Am I going to have an issue? Am I, like, your point is valid. Your point is very valid that save us from using the smaller 90 degrees conductors. Your other point was valid that if you heavily load those, then yes. But I have a 20 amp circuit going to those outside lights. Let's look at the back door. That's the front lights. My backlights are now on, and they're compact fluorescence. That's 1.83 amps. The front lights are LEDs. You gotta love this. My front has more lights than my back. And my back is 1.43 amps because they're not LEDs. The front are LEDs and it was 1.1. And I have more light in front than I have in back. They're really dim. They just go along the walkway. So I know Bobby Joe was just talking the other day about, shouldn't we replace these back lights because they're getting kind of scroungy looking. They've been there since the house was built. And yeah, probably. And I'd probably put LEDs in with the nice yellow glows. Or maybe those LED, color changing LEDs, so I can make them like red, or during Christmas, I can make them red, green, red, green, red, green. That would be cool. But in any case, I'm at 1.43 amps on my backlights. I'm only at 1.1, and those are those are fluorescents. But I think that 10 amp circuit is targeting those types of branch circuits. And just think, if I had a 10 amp twin downstairs where I can take one spot with two breakers at 10 amps, cat's meow. But here's the problem, Dawn. I don't have a GFCI and I don't have an AFCI. If that stuff goes in the code and if there's a market, I'm sure breaker manufacturers will probably go, maybe we should have a 10 amp AFCI and a 10 amp GFCI. All right. What's Willie? Steve says, excellent point for larger commercial and industrial installations, Dawn, and the materials in contact with the circuit will be warmed at the cost of the resistive heating elements. Yeah, you increase and you use those conductors at their higher, close to their ampacity values. You're going to push it. You're going to create some heat. Absolutely. Willie, lighting has become so efficient. I did a whole fire station with the whole building turned on. It was running 9 amps. Yeah. I tell you, Willie, the lighting, if there's any place that we can save money and infrastructure costs, especially with the 10 amp breaker and the 10 amp conductors, I would argue it is in lighting. Now, here's the challenge that you will create. You won't create an ampacity issue. You won't create a termination issue. You're going to create a challenge of, I can put everything. You have all the lighting on 9 amps. So you could put a 15 amp circuit breaker to cover all of that lighting. But if that breaker trips, you lose everything. So what you would then have to make a decision on is, how do I break up my branch circuits in a way such that if I turn that one breaker off, it doesn't kill the entire building. So now I think that as electricians, as designers, we're going to have to get smarter on what lights do we put on which circuits. And then maybe I throw in a receptacle in there too. I don't know. Or maybe we don't. Maybe we just keep all the lights on a separate circuit, keep all your receptacles on separate circuits, and I can reduce my infrastructure if I do that approach. All right, ladies and germs, cats and jammers, I thank you, Laurel, and I enjoy the engagement of talking to everybody online, because now I'm not just talking to a camera. I'm sitting in my kitchen. Maggie is laying below me on the floor here, and she is healing well, and I'm talking to a camera as if I'm talking to somebody. Talk about awkward, okay? So the interaction, and I love the questions. I love to watch the chats. Thank you for being engaging and including the discussion. So I hope everybody's getting something out of these sessions, and we are becoming masters at Ampacity, because it's very critically important that we make the correct conductor and circuit breaker combination selection to ensure a safe installation. All right, everybody. Until next time, next week's going to be tough. I will continue. So what I got to hit next week is motors. I've got to get over to motors. I feel comfortable with services. I think it's very clear, and I love the table. We're going to take a look at motors next because I think there's another opportunity. Willie, I appreciate you. Thank you very much. Thanks, everybody, for dialing in and
I didn't get that.
and joining me. So take care, stay safe, and we'll see you next week. See you next time on our discussion around ampacity. Take care. Thanks, Steve.